Hi, my name is Jonny Wu, and on behalf of my co-authors, I'd like to give a live recorded presentation of my AGU talk entitled Northwest Pacific-Izanagi Plate Tectonics since Cretaceous times from Western Pacific Mantle Structure. East Asian plate reconstructions contain large uncertainties due to lost and subducted oceanic lithosphere. Here we can see a large gap shown by the gray area between the existing Pacific plate and Eurasia at 100 million years ago. This gap approaches 6,000 kilometers at this time. Showing the continental US for scale, we can see that this knowledge gap is extensive. To understand what might fill the plate reconstruction gap, let us briefly review what a complete ocean basin age sequence looks like. The figure on the left shows the Atlantic basin in terms of seafloor ages. The youngest seafloor is colored red, whereas the oldest seafloor is colored purple. We can see a complete ocean basin age sequence formed by an intermediate seafloor spreading ridge of youngest ages and a rift flank with ages that get older away from the ridge. The conjugate rift flank has the reverse symmetrical age pattern. Looking at the Pacific plate, we can see the oldest part of the Pacific plate in purple, called the Pacific Triangle. Looking towards Western North America, we can see decreasing seafloor ages and a spreading ridge in red. These indicate that at least half of the ocean basin has been preserved. Presumably, the conjugate rift flank has been subducted under Western North America. At the Western Pacific, we can observe decreasing seafloor ages that abruptly terminate against the Western Pacific subduction zones. Based on ocean basin plate tectonics, we can infer that some of the Western Pacific plate, which is colored green, yellow, and possibly red, is missing. Secondly, we can infer that a spreading ridge has likely been subducted. Finally, the conjugate rift flank, which has been named Izanagi, is missing, and the size is unknown. In this study, we aim to reconstruct the missing parts of the Western Pacific in the fully subducted Izanagi plate by looking into the mantle. We use a technique called slab unfolding, which is the structural restoration of a slab back to its initial pre-subduction size. We apply this technique to MITP-08 global tomography and FWEA full waveform local tomography. A number of other global tomography are also considered, including UUP07 and GAP-P4. We will input our unfolded Western Pacific slab into a global plate model. Following ocean basin plate tectonics, we will infer the Izanagi Pacific spreading ridge was located at the leading edge of our restored Western Pacific plate. Having reconstructed the full Western Pacific plate, we will then model the lost Izanagi plate in green as its conjugate rift flank. Finally, we will test our plate model produced from tomography and seafloor spreading against Eurasian magmatism, which is independent from our plate model inputs. To unsubduct the Western Pacific slabs, we first map the slabs in 3D to build a spatially self-consistent model. This step is not shown here. We then go to tomography and pick the Western Pacific slab edges from tomography by considering that higher gradients are indicative of slab edges. Our use of tomographic gradients, shown by clustering of the velocity contours in the tomography, reduces the emphasis on the chosen color bar. We then unfold the slab to the Earth's surface using area conservation. In this step, we assume an initial oceanic lithosphere thickness. The slab areas are unfolded by depth to allow us to apply a depth-dependent density depth correction following the Prem Earth model. Here we can see that area 1 is unfolded back to an initial assumed oceanic lithosphere thickness, followed by area 2, area 3, area 4, and so on and so forth. In the next slide, I will also show a way that we can correct for possible tomographic image blurring in this study. There are a number of uncertainties, and we consider these effects of variable initial oceanic thicknesses, so changing varying the thickness that we're unfolding to, picking slab edges using computed isosurfaces, and unfolding slabs from other tomography models. These alternative analyses are included in the error ranges in our results that are shown later. Image blurring, known as tomographic smearing, may exaggerate the apparent slab volumes. This is shown by the blurring of the word focus on the left. We estimate the potential tomographic smearing in MITP-08 by looking at synthetic slab resolution tests. In this test, an assumed velocity structure is input and inverted using the available tomographic resolution, ray paths, and stations. The output image here shows a 25% increase in the slab area relative to its true size. To mitigate the effects of tomographic smearing, we decrease our unfolded slab volumes according to the available tests that we analyze. These tests show a mean 25% smearing effect. And we found minimum and maximum ranges of smearing of 10% to 40% respectively. We will unfold our slabs with these 3 corrections, and we will call these our mean, minimum, and maximum cases. We unfold the Western Pacific slabs from Kamchatka down to the Southern Marianas along 14 transects. This map shows their unfolded slab lengths using our mean case estimate for the lost Western Pacific plate. We progressively unsubduct the Western Pacific slabs, pulling them out of the mantle by attaching them to the Pacific plate and reversing the plate convergence over time. At 30 MA, we find that the leading edge of the unfolded slabs continues to overlap Eurasia. By 55 MA, we find that the leading edge of the unfolded slabs fits well with Eurasia. And if we keep pulling, by 85 MA, the slabs underlap Eurasia. Consideration of various uncertainties gives a wider range for the best fit time at 55 plus or minus 15 MA for the intersection of the leading edge of the slabs with Eurasia. We consider that the combination of the existing Pacific plate and our unfolded slabs now represents half of an ocean basin. Following our approach, we reconstruct the Izanagi Pacific spreading ridge at the leading edge of our restored Pacific plate. At first glance, this seems to be a reasonable choice because of documented magmatic and geologic evidence for ridge subduction at this time, including a 56 to 46 MA magmatic gap that was documented in the paper Wu and Wu 2019 in geology. We now reconstruct the Izanagi plate as the conjugate rift flank of the Western Pacific plate. The Izanagi plate is shown here in green, and we can see that the age isochrons reflect are the reverse symmetric pattern from the Western Pacific plate. The age isochrons shown here were adopted and modified from Mueller et al. 2016. We input our reconstructed Western Pacific and Izanagi plates into a global plate reconstruction. This movie shows the reconstruction. After 52 MA, we merged the East Asia plate reconstruction of Wu et al. 2016 to provide a more complete picture back to the present day. I'll now play the movie. Our plate reconstruction at 75 million years ago shows one of the more testable features of our plate reconstruction. The southern limit of the Izanagi Pacific realm is a sinistral transform that we name the Qingdao line, since in our mean case, this transform intersects Eurasia near Qingdao, China. Here shown on the right, the extensively used model of the Sydney group shows similarities to our solution, which is very good. However, it differs in terms of the southern limit of the Izanagi plate. Our reconstructed Qingdao line, shown here on the Sydney model, suggests that South China and Southeast Asia, which have been reconstructed within Izanagi in this model, may not actually belong within the Izanagi realm. On the next slide, we test our plate model against Eurasian magmatism. Here, the map on the left shows the igneous rocks of the Eurasian continental arc. We superimpose our reconstructed Qingdao line on this map. Our plate model predicts that the Izanagi plate was subducted north of the Qingdao line, whereas at South China and Southeast Asia, these areas were within a different subduction realm that was not Izanagi. Our compiled magmatism from Japan and the Russian Far East, shown at the upper right, shows a distinct magmatic signature with abundant magmatism and enriched isotopic values from around 100 to 56 million years ago, a distinct 56 to 46 MA magmatic gap, and magmatism after 46 MA that shows depleted isotopic values. In contrast, when we look at magmatism south of the Qingdao line, areas in South China and East Asia show a very different magmatic signature. We see magmatism that abruptly stops around 80 million years ago. And this pattern continues further south into Southeast Asia. We are also not aware of any evidence for ridge subduction along these southern areas during the early Cenozoic. Going to the early Cenozoic, our plate model predicts Izanagi Pacific ridge subduction along Eurasia, but this is limited to north of Korea only. During the 50 to 43 MA Pacific motion change, we predict that this Qingdao line transform becomes a subduction zone. The subduction initiation along the Qingdao line transform forms the Izubonin Marianas arcs and possibly links to fault reorganizations within the Bohai Bay Basin in China. Here we conclude with a slide of the main findings from this study. Our reconstruction of the Northwest Pacific and Izanagi plates from mantle structure fills an important gap in Pacific Panthalassa plate tectonics. It further implies the size of the adjacent realms Kula and the poorly known area between Tethys and the Pacific realm that has been called Junction. Thank you very much.